Hi, my name is Julia Bush, and this is my presentation for Lab 3. So as an introduction, the point of this lab was for us to observe the effects of a small cylindrical magnet, the effects of its field on a sensor in our phones using an app, and by observing the change in the overall magnetic field caused at first just by the Earth and then by the Earth and the magnet, we could then determine the magnitude of the magnetic dipole specifically, and then specifically its moment. We can determine from that. And then some concepts that we explore in this lab include the magnetic field of magnets and magnetic dipoles and their moments. And so the equation we used for this lab was that the magnetic field of the bar is equal to a constant times the distance to the power of another constant. So in order to find this constant, we did a lot of measurements, a lot of trials where we would have the magnet on axis with the sensor in our phones, and then also 45 degrees off axis and perpendicular in order to determine the change in the magnetic field overall. So then by taking the ln of this magnetic field component in the x direction and then the natural log of the distance, we could then find the constant as mentioned previously in that equation. And after we found that constant, we could then find the approximate magnetic dipole moment, which I calculated to be about 7.4 amp meters squared. So for the coding portion of this lab, we created a model of this small cylindrical magnet and its field. So we had arrows on the axis of the magnet perpendicular to the axis and then at a 45 degree angle from it. So the ones on axis you can see point into the south pole of the magnet and out of the north pole, and then perpendicular they point in the opposite x direction in order to display this kind of looped effect of the magnetic field. And then you can see in the 45 degree distance angle that the arrows point up and out and then down and out from the magnet, and this reflects this looping model and this looping characteristic of magnetic dipoles. And here's the equation we used to calculate the magnetic field in our code, the constant times 1 over the distance squared, and then using the dipole moment and the distance we could calculate the field. And these are the actual results that it calculated for these fields. And so some concluding thoughts and observations are that I observed that as the magnetometer on my phone became closer to the magnet, the measured x component of the magnetic field became higher, representing the higher magnetic field with a lower distance, which is why r is in the denominator for the equation. And then if I had lined up the meter stick, instead of lining it up north and south like we did in the experiment, if I had made it some angle, it would have changed the trigonometry of the calculations in finding that magnetic field, but it would not affect the magnitude of the dipole moment. And similarly, if I had used two magnets lined up end to end, the ends would still have polarized like as a north and a south pole, and then should therefore yield the same results in relation to the dipole moment, and as well as the magnetic field should end up being pretty similar. So that's all I have for this lab. Thanks for listening.